Hello, in this lecture we will review the atomic structure and electron configuration. At the heart of every atom lies the nucleus, a dense center composed of protons and neutrons. While the nucleus holds the majority of an atom's mass, today we're shifting our focus to the electrons, the tiny, negatively charged particles that orbit the nucleus, which are illustrated as red particles in the animation. These electrons are not just randomly scattered. They occupy specific regions called atomic orbitals, where they are most likely to be found. The arrangement and behavior of these electrons determine many of the chemical properties of an element. So, why do electrons occupy specific orbits or energy levels? This arrangement is due to the electrostatic attraction and repulsion between the negatively charged electrons and the positively charged proton in the nucleus. For example, electrons repel themselves because they have the same negative charge, whereas electrons and protons attract each other because of their opposite charge. However, electrons can only exist in certain energy levels, which are defined by the amount of energy they have possesses. When an electron absorbs energy, it can jump to a higher energy level, further from the nucleus. This is called excitation. Conversely, when an electron loses energy, it falls back to a lower energy level, releasing energy in the process. The ground state is the lowest possible energy state that an electron can occupy in an atom. This release of an energy can often be observed as light, which is how we see phenomena like glow of neon signs. These energy levels are organized into shells and subshells. The first shell is the closest to the nucleus and has the lowest energy, while the outer shells have progressively higher energy levels. The electron configuration is a way of representing the arrangement of electrons in a ground state atom's orbitals. The filling of these orbitals follow a specific order known as the Aufbau principle. According to this principle, electrons occupy the lowest energy orbital first before filling higher energy levels. The order is 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, 5f, 6d, 7p, and so on. Additionally, according to the Pauli exclusion principle, no more than two electrons can occupy the same orbital, and electrons, represented by arrows, should point in opposite directions, indicating opposite spins. For example, let's look at helium. Helium has two electrons. According to the Aufbau principle, the first electron should fill the lowest energy orbital first, and according to the Pauli exclusion principle, the second electron will also occupy 1s orbital, which is the lowest energy orbital, and has the only one electron, meaning that there is a space for another electron. Therefore, its electron configuration is 1s2. This tells us that both electrons are in the 1s orbital, which is the lowest energy orbital. Now, we take a more complex element like phosphorus, which has 16 electrons. The 2 electrons fill 1s orbital, 2 electrons fill 2s orbital, 6 electrons fill 2p orbital, 2 electrons fill 3s orbital, and 3 electrons remain. However, according to Hund's rule, every orbital is singly occupied before any orbital in that level is doubly occupied. So, instead of forming doubly occupied, singly occupied, and unoccupied orbital, it forms a 3 singly occupied 3p orbital. Thus, its configuration is 1s2, 2s2, 2p6, 3s2, 3p3, and this is how they are filled. This notation can become quite lengthy, so chemists often use a shorthand version called noble gas configuration. To simplify the electron configuration for elements with many electrons, we use a method called the noble gas configuration. This technique uses the electron configuration of the nearest preceding noble gas to represent a portion of the configuration. For instance, instead of writing out the full configuration for phosphorus, we can simplify it using neon, the nearest noble gas before phosphorus. Its full configuration of 1s2, 2s2, 2p6, 3s2, 3p3 can be written as neon 3s2, 3p3. Here, neon represents the electron configuration of neon, 1s2, 2s2, 2p6.